Hey folks, thought I'd do a Sunday morning science with superconductors. I've got a couple experiments set up here. Let's check this setting out. I got my liquid nitrogen here in this styrofoam cup. And then in this desiccator, I have some discs that have superconductors embedded in them. It's a real thin disc. I have to keep it in this desiccator. Asfara, how you doing? Thank you. Hey, so these discs, they have tiny superconductors, like a thin superconductor, a thin strip of a superconductor inside them. So you can't really see the superconductor itself. I have to keep it in this desiccator because the superconductor itself has to stay dry. And so this material down here takes moisture out. So let's just take one of these and play around with it. So I'm going to get a magnet. Let me get a magnet. Hi, Sheba. Thanks for the hearts. And I'm going to take this magnet here. So I've got these magnets here. Oh, they're really strong, so it takes a bit to separate them. Man, are those strong. Of course, my table's magnetic, too. Hey, Jamie. Welcome. So I'm going to take this magnet and place it on top of this disc that contains a superconductor. And you know what? I can tell that my table's a bit magnetic here, ferromagnetic, so I better try this experiment with a brick on top just to reduce any magnetic effects that might be coming from the table. If I place this magnet on top of the superconductor, nothing's happening. Because what we need to do is we're going to need to cool the superconducting material to below its critical temperature, which is 93 Kelvin. You know, I think the table's just magnetic because it's just got some iron in it. It would be my guess. Or steel, you know, iron from steel. And so this is a YBCO. It's made of yttrium. Well, you can't see it. It's inside. It's made of yttrium, barium, copper, and oxygen. Sometimes it's called an YBCO superconductor. And its critical temperature is 93 Kelvin. And so this is going to need to be cooled below 93 Kelvin in order to show its superconducting effects. So that's why I'm placing it in the liquid nitrogen to get it to cool. Hey, Siraj, how are you? We're trying to cool our superconductor here to below its critical temperature, which is going to be 93 Kelvin. Liquid nitrogen, of course, is going to do that trick for us. I'll take it out, and we'll place it on this black brick. And now I'm going to place this magnet on top, see if I can get this to work. Oh, it's close. Let's see here, see if we can get this just right. I'm doing fine, Siraj. Come on, baby. See if I can get that to work. Oh, it warmed up too quickly. Let's try a bigger one. Might work better with a bigger one. Well, I hope this works. Pop it in. My YBCO superconductor. Wonder if the table's going to screw things up. We are. Well, I'm not making superconductors. Moonlit, I'm just messing around with them. I wish I knew. Well, I think I know how to make them. Hey, thanks, Sheba. That's really nice. Welcome, Storm Viper. We're cooling some YBCO superconductors to below 93 Kelvin. We got them at 77 Kelvin. You can see when they stop boiling really quickly, you know that you're at 77 Kelvin, the same temperature as the liquid nitrogen. So I'm going to pull that out. Nice. I hope your PhD goes well. Hello, Nora. Place this on our makeshift. Love you too, Maddie. All right. Let's pop this on here. Hope I can just balance it just right. Boy, that's not working real well. Huh. I wonder if my tables, I hope you do well on your chemistry exam. I'm wondering if my table is messing things up. Let's try this over here. Just see if we can pop, yeah, that's gonna work. There, we got it working. See that? Look at that, man. Isn't that crazy? Let's turn that, I'm gonna just try to pinch it on there just a little bit to get it a little tighter. And then of course, if we turn it upside down, the dadgum thing still sticks. Oh, they are cool, Nora. I'm from the United States. Yep, so we're gonna have zero electrical resistance flowing through flux tubes. There's some flux tubes set up. So it's type II superconductor. There's a thin disk here, and there's tiny impurities embedded in that disk. Hi, Maddie. And those impurities are where the magnetic field penetrates. They are incredible, Moonlip. All right, let's take this one over here. Pop this one on. My tongs, of course, are magnetic. Pop that there, and look at that one. Isn't that crazy? That's just nuts. And what's funny is that the superconductor, woo, a little nitrogen popping off there. I don't know if you see that. Can I make a rail out of them? Yeah, we'll do that in a little bit. I have a track. How much weight? I don't know. Let's find out. Let's figure out how. I don't know what. Let's see. How would I do that test? I think I have a little styrofoam cup here. I could put a little water in it. Yeah, let's leave these right here. I'm going to leave these right here so you can sort of see as they warm. You'll notice. I think this one's warming. As they warm, you'll notice. Thanks, Sheba. As they warm, you'll notice that they'll get below their above their critical temperature, and they'll no longer be able to show their superconducting behavior, and then they'll just kind of gently fall onto the magnet. Sometimes you can see that happen. Let's just change the perspective of the camera just a bit here. There you go. All right, let me go get a, I thought I had some styrofoam cups I can fill with some water. Oh yeah, this one here. I'll fill this with a little bit of water. And then we'll see if it can hold that weight. First, we'll just put the cup on just like this. Why not? Oh, that's a little tricky. Huh. That's a little tricky, but it's... Ah! This one's probably going to be the better one that we want to use. Yep. It is cool. Let's get a little water in there. See how much it can hold. Hold on a bit. Let me get a little water. My bag of tricks over here. My cabinet of tricks. All right. Pour a little water in there. I think I'm going to need to cool it down again. Yeah, this is a painted black brick. Sorry I missed your name. I just popped in here again. I am messing with superconductors. So these discs contain my magnetic tongs. Oh, I'm just going to grab it. Don't tell anybody. These magnetic tongs, these discs here contain thin wafers of a superconductor embedded into them. It's a YBCO superconductor made of yttrium, barium, copper, and oxygen. And they also have some impurities embedded in them as well. And if you can cool the superconductor, I should say the material, to below its critical temperature, then it becomes superconducting. And superconducting materials show some interesting effects when they interact with magnetic fields. Hi, Aiden. So we're going to pop these thin discs that have a superconductor wafer in them, and we're going to place them on these magnetic fields and see what happens. That's right. We're going to see if we can't get this cup to levitate. Oh, nice. Here we go. There it is, up above the magnet. Levitating just fine. Of course, it's going to be able to easily hold. I want to use a bigger one. Let's get this bigger one. Pull it out. I should have got plastic tongs because my tongs keep messing around with the magnets I'm using. There we go. Pop it on there. I agree. Ah! Tongs. Let me get these gloves. This might work a little better if I get these gloves. Why does it levitate? Oh boy, here we go. This is going to be tough to describe. We can work on it though. So it looks like I got it levitating here. We'll get into that in a bit. I have a the description of why these levitate is complicated, and I'm not completely sure that I understand it 100%. But I do have a long form video on this. If you just go through my long form videos, I have one called Quantum Locking and Superconductivity Explained. Hey, thanks, MD. That's nice. Look at this. I'm pouring water in there and it's still levitating. So I'd recommend going to that long form video to get some insight into why the superconductor levitates. Look at that. How much water's in there? I got about a quarter of the bottle put in, and it's still levitating above. They are really cool, Moonlit. Thank you, Siddharth. Okay. Yeah, that fits right on there, man. Thanks for that suggestion. I want to see, I want to see, it should stay on there until the superconductor, yes, this is quantum locking. It should stay on here until the superconductor is warmed above its critical temperature. And its critical, and its critical temperature is 93 Kelvin. You can kind of see it's weakening a little bit. Yeah, I agree, Moonlit. If only they didn't have to get cooled to below their temperature. Here's my dog I brought up to work today. This is Ruby. How you doing, Ruby? There she goes. She just wants to be petted. Okay. So yeah, we can sort of watch as this loses its superconductivity as it warms above its critical temperature. Look at that. Isn't that just beautiful? Manette, it would stay superconducting as long as it's below its critical temperature. I think they've done some experiments to have something remain superconducting for several years, several decades, maybe even half a century or so, which is pretty remarkable. Yeah, so this contains a Type II superconductor made of yttrium, barium, copper, and oxygen. Whee! It's right, Asfara. Look at that. And this is commonly known as an YBCO superconductor, YBCO. Its critical temperature is 93 Kelvin. As long as it remains below 93 Kelvin, it will enter the superconducting state. That would be Moonlit. I think they have a superconductor that, yes, the Moebius strip superconductors are awesome. I'll get to what's a superconductor in a second. They have had a room temperature superconductor, but it requires enormous pressures. As far, I do not know what a Type I superconductor is made of. If somebody might get into, Google and maybe, comment on the difference between Type I and Type II. I think it might be made of the same thing. The difference with the Type II superconductors is that they have impurities embedded into them. So let me just go over here and draw what I mean so you can get an idea of this. I got a bunch of gunk here on the board. So we can talk about, what's going on with these Type II superconductors a little bit. I got to erase this board a second. So let me just make sure I got the right perspective here real quick, because this is interesting. Let me just see. So I got it. Okay, so I want to go right below the word violets. So there's a disc. There's a black disc. I'm just going to check out and make sure that this looks okay. Yeah, that's okay. All right. So in this black disc, there's a really, really, really thin wafer of the superconducting material. And the disc is just to protect it so I don't break it. This is the YBCO material, YBCO. Yttrium, barium, copper, and oxygen. And what they do is they put impurities, they embed impurities into the superconducting disc, like this. This is the way we're going to imagine it. And here's the deal. We're going to draw, here's our magnet down here, right? This is our magnet. And there's, of course, magnetic field lines coming up off the magnet. And the interesting thing about superconductors is that they repel magnetic fields. So in the absence of these impurities, the magnetic field would have to bend around the superconductor like this. And in order for the superconductor to actually touch the magnet, what would have to happen if that were to occur is the magnetic field would actually penetrate the superconductor. And that can't happen because superconductors repel magnetic fields. So what's going on with the Type II superconductor is that these impurities are not superconducting. And so the magnetic field lines, they can penetrate through the impurities. So you got one coming here and it can penetrate through the impurity. And that happens all over the place, right? These magnetic field lines penetrate, they bend and penetrate through the impurities. Because superconductors, the superconducting material, expels the magnetic field. So this is going to expel it. I can't go through here, I got to go through here, and there's where it goes. Now what you can imagine is, once this happens, this is locked in place. Because in order for this to move, you know, this field line going this way, if I push this way, the magnetic field then is going to go through the superconducting portion of the material, and it can't do that. And so that's a simple, quick explanation of how the superconducting material works. Those little areas where the magnetic field penetrates, they call these flux tubes, because what ends up happening here is you get current of electrons going around these. And the current that's going around here is, going with zero resistance. So they call these flux tubes. Yeah. So here's the effect. Well, you can see this superconductor has been now warmed above 93 Kelvin. And so it's no longer superconducting. In order to get it back to the superconducting state, you're welcome, Sheba. Oh, sorry. To get it back to the superconducting state, we're going to drop it in some liquid nitrogen to cool it. So I'm going to just scroll through the comments here a little bit to see if I missed anything. Oh, I can't find them. Well, that should have cooled this below 93 Kelvin. Let's get a little more in here just to cool it down. Get them below get them below 93 Kelvin. That's a critical temperature of a YBCO superconductor. And then once those are nice and cool, which I can tell they are because the liquid nitrogen is not boiling rapidly anymore, we're going to pop them on these magnetic fields here, and we're going to see what happens. Actually, let's get the magnetic track set up. What do you say? Let's get the magnetic track set up and do that instead. I'm going to move this out of the way. And we'll get the track set. Put this here. Get my track ready. Because there's some interesting experiments you can do with the track. So I'm just going to change this perspective just a little bit. It would be easy, MD, to do that, but I seem to be having trouble with that experiment in this case. I think it might have something to do with my table, which you can see here is quite magnetic. You see that? These magnets are sticking to my table. So I wonder if that's somehow influencing that experiment. Let me get the track set up. I'll try it again in a little bit. So here's the magnetic track. Whoop. Right there. Get that all set up. Let's back it up a little bit. Hey, Matthew. There we go. I'm going to back up just a bit so we can see the full track. All right. There we go. Let's put the superconducting discs onto the magnetic track, and let's see what happens. Let me get my gloves on. Pop one out. Pop a disc out. There we go. Pop it on the track. Give it a whirl. There it goes, baby. Come on, that's cool. That is just really cool. Now, you might wonder how in the world can it move if, you have these magnetic field lines penetrating the impurities. Well, in this case, all along the track, the magnetic field is uniform. So to the superconductor, it doesn't see a difference between this position on the track and this position on the track because the magnetic field is constant all along the track. It's that change in magnetic field that the superconductor is going to resist. So you can show this pretty easily. What I'm going to do is I'm going to take one of these magnets and I'm going to pop it on the track and you can watch what happens, all right? So notice by placing a magnet on the track right here, I'll change the magnetic field right here. It's going to just take me a bit to get this magnet off. Oh, man, is that hard to get off. Come on, baby. There, I separated them. Okay. So I'm going to place the magnet right there. Boop! Oh, well, that's stopping because of the... Yeah, we'll get this going. Ready? Now notice I've placed the magnet right here. Get that going. Boop. Well, that didn't work like I thought it would. There it goes. You see that? It resists going through here because the superconducting disc is going to resist going through places where the magnetic field changes. Oh, it slowed down just a bit. Let's keep it going and watch. Right about here. Click. See that? It will resist going past this point because this is a place where the magnetic field changes. There it goes back in the other direction. Yeah, I'll try placing the magnet on top of the superconductor. I hope I can get this to work. I had a little trouble earlier. Maybe I should use my square disc over here in the desiccator. Let's try this one. See if I can get that to work. Pop it in. They might be too wet. That happens sometimes. Pop it here and just see. Yeah, I don't know what the deal is today. Having a little issue getting this going. We'll try her again. We'll give it a shot. Let's get this cooled down. We'll try a couple of them. Maybe if I put these up here, this might work a little better. Keep it a little higher up off the desk. All right, let's give her a shot. Ooh, that's cold. Right there, like that. Okay. Let's hope for the best. Maybe it was upside down. I think that was it. That was it. That was it. That's the trick. I can tell. Look at that, folks. There it is, baby. Come on, that's cool. Come on, that's cool. That's what I did wrong. That is just unbelievable. It is extremely cool. There we go. Ah! Off it goes. That's what I did wrong. I forgot I have to turn them upside down to do this. Let's try her one more time. There it is. Look at that. Isn't that crazy? I'm trying to get it to spin. It's really interesting trying to get this to balance. You've just got to get it right in the spot where the magnetic field isn't going to change. Hey, Ruby, my dog's here. Come on, baby. There we go. Thank you, Manaswi. I will try that. He suggested, or he or she, whatever, suggested to just blow on the magnet to get it to spin. I've got to get it to levitate here first. That's a great suggestion. There we go. Oh, I had it. I'm wondering if it's, there we go. Look at there. Okay. All right. Here we go, and I'm going to blow on it. Oh, you can see the superconductor had been warmed now above its critical temperature, and that's why the superconductor just fell. Oh, XCX7. Let's try getting one that's already cooled. This time, stupid me is going to remember to turn it upside down. I do too many experiments, and I can't remember what to do all the time. There we go. Pop it there. Place my superconducting disc, or my magnet on top. Try to get her to balance. Come on, baby. Come on, baby. You can do it. Come on. Yeah, it's, oh, you know what? I wonder if it's, that's just too close. Man, I'm having trouble. There it goes. There it goes. Look at that. Isn't that beautiful? Just crazy. This is the Meissner effect. The superconductor in the disk is repelling the magnetic field from the magnet that's on top, and it's causing that superconductor to levitate. The magnet dance. Yeah, I am a chemistry teacher, XCX7. Hello, Mix. Yep, we got quantum locking engaged, Moon. It's going on, baby. And I'm just going to leave that there. Use a straw. All right, we're going to try that. We are going to try to use a straw. Let's see if I got one in my bag of tricks up here. Hold on. Oh, there we go. Might watch as that superconductor warms above its critical temperature. That magnet will probably fall. Let me get a straw. What a great suggestion. Let's hope I can do this. All right, let's see. Boy, that seems to be locked. It does not want to move. Wouldn't that be awesome if they would be at like room temperature? Harriam, hello. Hello, Mix. I love them. You can see, all right, you can see it's warming up and it's above its critical temperature, getting awful close. And you're going to see that magnet just sink right onto the superconductor as it warms above its critical temperature. Let's get a fresh one out here, one that's nice and cool. Pop it on there. Yep, that one's done. I'll try this one. Get this magnet out of the way. Oh, come on, baby. Man, just got to get it to balance just right. Oh, I think I got it. No? Come on. There it is. For some reason, it wants to go to the side. I don't understand. Let's try this one. No, that one doesn't seem to be working real well. Let's try the smaller one. Let's try the smaller one. The smaller disc. I'm getting frustrated. Yeah, I'm having trouble, y'all. Having lots of trouble. Just can't seem to get it. Yeah, it could be because of the table. Let's try this. Let's really get this far from the table. Let's do this, huh? Let's get it as far as I can. That might be it. Oh, yeah, I think that's going to be the trick. The table is made of iron, which I think is affecting the experiment. I think this is going to be the trick. We're going to stick it. This is way up far from the table. I think this is going to do it. It just feels easier up here. It also looks kind of there. Looks kind of cool. There it is. There it is, baby. You can put the superconductor in a small dish with the liquid nitrogen so you can use it while it's cool. I could try that. I sure could. Let me get these other ones cool. Cool down. Just pour it right on there, eh? Pour it right on there. That's going to be fun to watch. Just pour it right on there. You know that looks cool. That should cool it down. Let's see if that cooled it down enough. Sure did. Sure did. Superconductivity, the Meissner effect. Ah, that's just awesome. And now you can see, you see that? That's so cool when that effect happens. You can see it frost over. And when it frosts over, the superconductor is warmed above its critical temperature, and then the magnet drops because the disk is no longer superconducting. I love that effect when it happens. It's really neat to see. Let's see if we can get that again with the larger one. The larger ones take a little longer to, they take a little longer to frost over. Boy, they're harder to get the magnet stuck on there, though. Look at that. Holy cow. That's frickin' cool. Let me try to blow this, see if we can get it. Come on, baby! That's awesome. Look at that. That is just beautiful. That is gorgeous. Oh, now you can see it's warming. You see when it frosts over, you know that the superconductor is warming. Yeah, I'm not sure it's going to... Oh, yep, I don't think it's going to levitate there. Well, I'm glad you feel like that, Mix. Why do I like chemistry? You know, I like all science. It really doesn't matter to me. You know, look at the way that just the frost, or not the frost, but the condensed water vapor just pours out of the disk. That is such a beautiful effect. Here it's a little too high. I can't get it to spin. It's gorgeous, though. It's a really pretty experiment. So again, I've got our superconducting disk right here. It's a Type II YBCO superconductor, cooled below its critical temperature. And so we've got this magnet that's levitating above it because superconductors expel magnetic fields. Moonlip, you are correct. Science, more than anything I know, brings out the kid in me, and I know it does that for a lot of people too. So I'm glad you're of like mind. We got this rolling, folks. I finally got this figured out. Thanks for hanging in there with me while I tried to, look at that, tried to get her going. That's beautiful. And let's see, there it goes, you see? The superconductor warmed above its critical temperature. It's no longer superconducting and it can't, repel the magnet anymore. Let's get one that's been cooled. So here I've got these being cooled in liquid nitrogen. So I can grab another one and place it on center stage. I'm going to have to get some more liquid nitrogen out at some point. I'm running low. Let's pop this one up. This one warms really fast. So if I'm not quick, I'm not going to be able to catch this. But there it is. A little nitrogen boiling off. While that's going, I am going to get a little more liquid nitrogen. You might be able to watch this frost over, and as it frosts over, it's losing its, it's warming. And if it warms above its critical temperature, there it goes. It loses its superconducting ability, and the magnet no longer levitates at that point. A little more liquid nitrogen. All right. Got it in my styrofoam cup. We're gonna, yes, the elephant's toothpaste reaction, that's just a fun one. I've got a video on that one. What I like to do, if you look at I have a video called Harry Potter and the Elephant Toothpaste Potion. So what I like to do, after you generate the foam in the elephant's toothpaste reaction, you take a wooden splint and you pop it into, light it and pop it into the foam, which contains oxygen. The splint just lights up like a light bulb. And I say, Lumos, when it lights up. Like the Harry Potter charm. People seem to like that experiment. All right, let's take this, pop it here on our center stage. Manaswi, I don't know if I've seen Now Red's experiment where he made superconductors. I'm not a synthetic chemist, so I'm not a chemist that sort of makes new materials, so I've never made a superconductor myself. I'm more of a physical chemist. Whoa! That popped right off. Expelling the magnetic field, baby. So the type of chemistry I do, I just do stuff to understand. So I use chemical and physical principles to try to understand what's going on. That's sort of my approach to chemistry. Man, that's just not, that is really popping off of there. Wow, that's having trouble. Come on, there it goes. I got it. I got her going. Hey, welcome, Flatline. We're going to see if we can't get this thing rolling here. There it goes. Come on, baby. That is beautiful. CX7, I don't make medicines. I'm not a synthetic chemist. Yep. Sylvia, I agree. That is cool. Definitely cool. And I like the way the condensed water vapor just kind of flies off of it as well as the nitrogen. Some of it gets embedded in this and it evaporates off. Hey, Ruby, my dog's here. She came up to work with me today. How you doing, buddy? So I'm going to get the second one out while this one starts to warm back up. Going to get her another one ready. Oh, did you check it out, Moonlit? Thank you. Thanks for checking it out. Leave a little comment on that video so I can see you again. That'd be cool. Ooh, let's see. We'll get this cooled one. Oh, then the Murray, no, I do not do a live daily. I've just started experimenting doing lives on Sunday. It's Sunday morning here where I live, so it's roughly this time. Sorry, there's a couple comments I'm trying to catch up on here. Will it work if you put a paper in between it? What makes it spin so fast? And yeah, it's a buffet of oxygen. Yeah, let's get a little piece of paper. Somebody commented, get a little piece of paper. And we're going to try to put that piece of paper in between the magnet and the superconducting disc. So let's get one that's already been cooled here. Nice. Sunday morning, the Murray? Or is it more Sunday afternoon, Sunday evening, where you're at? There we go. That's definitely levitating. And then there, look at that. Look at that. Come on, baby. Oh, it got too warm. It's above its critical temperature. And the magnet falls, of course, because the disk is no longer superconducting. And I think what might be going on, 8:10 p.m., India. Nice. I've got a lot of friends from graduate school who are from India. You're going to have to forgive my pronunciations. I think he's from Gujarat, if I remember correctly. They never get old. Tell me about it. Ah! Let's try that again. Come on, stick. Or lock. I don't know what the term is to use. Quantum lock. Ah! So at some point, these experiments are going to get increasingly difficult because when water gets in the superconducting disk, in the superconductor, it absorbs it. They have a little trouble doing their magic. And so that's happening as I do these experiments, water is being absorbed by the superconducting disk, and I'm going to have to remove the water. I do that by placing it in that desiccator and just letting them sit, but that'll take overnight or so. Here we're going to put a piece of paper under there. Look at that. Look at that, baby. It's still working. So thanks for the suggestion of that experiment. See if you can't get it spinning. That is just beautiful when that happens. Look at the way it just, the beauty of science, man. I have a really big dewar of liquid nitrogen. You can see it there. I have a 20-liter dewar, and I also have a 55-liter dewar. And so I get it filled about once a month, and I have plenty of liquid nitrogen to do experiments. Yeah. There you go. It's spinning away. Look at the way the cloud vapor forms. It's really kind of nice. It's just a beautiful experiment. Is it possible to levitate magnet on a superconductor? That's what I'm doing here. And levitate superconductor on other... Oh, let me get to that. Got to find the comment again. I'm trying to. There it is. And levitate that superconductor and other magnets. Is it possible to levitate the magnet on the superconductor? I am doing that. And then levitate that superconductor. Okay, I see it. I see it. We're going to try. We're going to try this. I don't think this is going to work, but we'll give it a shot. So we're going to try to take this levitating superconductor, and we're going to try to stick it on this magnet over here. I don't think it's going to happen because the magnetic fields are going to just go crazy, but we'll give it a shot. Yes, it would be. Yeah, you can see, oh, man. Well, my superconductor, it warmed above the critical temperature, so we got to try this again. All right, hold on. Let's try her again. Let's get the big one. Get it out of liquid nitrogen. No, I'm not describing the Josephson effect, and I got to be honest, I don't think I've ever understood it. I don't think I'd be able to describe that, but I can kind of describe the Meissner effect, which is the repulsion of magnetic fields by superconductors. So the disk here, the disk here contains a superconductor, and it should repel the magnetic field by this. Yeah, Flatline, I have made ice cream with liquid nitrogen. It's fun, but I have to use way too much liquid nitrogen, and the ice cream doesn't really taste that good to me. I guess I'm not that good of a chef. We're going to try this one more time. So I'm going to try to take this and balance it on the track. Yes, boy, I don't seem to be able to get it onto the track quick enough. Yes, I did buy these. If you go to, I write a blog for something called the Chemical Education Exchange. If you go to that blog, and there's a blog there that I've written on, just go to the Chem Ed X. Yes, I did watch Breaking Bad. Go to the ChemEdX ChemEdX, ChemEdX website, and there is a blog post there called Quantum Locking and Superconductors. And in the references, I reference the company that I bought these from. I apologize, I can't remember the name of the company off the top of my head. They're very helpful. This system I bought is not cheap, but you can buy superconducting materials like this for, a couple $100. You won't get everything that you see here, but you'll get quite enough to be able to play with for sure. So we're going to try this one more time. I think I might be, my superconductors might be a little too wet. Ah! Let's try her again. Come on, baby. Come on, get on there. Yeah, they are really frosting over quickly. There we go. You can really tell they're frosting over really fast. Then Murray, if you go look at some of my shorts, I have a few shorts where I dress up like Walter White in one of them. Like 3 of them, I think. So check those out. Be sure to leave a comment so I see that you were there. One of them is doing pretty well. One of them's got like a couple million views. Where I did one where I explained the thermite reaction and how Walter White used the thermite reaction to break into that building with Jesse. That was a lot of fun. I shot that video with my son. He helped me. Really talented film guy. Okay. There we go. Oh, so Vamuri, you've seen that video. Thanks. There it is. Awesome. Yeah, we had a good time. That was a lot of fun making that. And I watched the whole series with my son. It was pretty crazy. Thank you. Thanks for letting me know you enjoyed it. All right. Moonlit, hold on. Let's see here. See if I can find some of these. Moonlit, just a smiley face came through. So, just a smiley face. Superconductivity. Got that superconducting disk here. That's, that's really going. Oh, there it is. That's correct. Thank you, Moonlit. Quantum Levitation is the name of the company where you can buy these things from. Let's try. That's funny. Dada, what are you thinking of? What are you thinking of using my name in? I mean, you're writing a book? What's your book you're writing on? What does it happen to be written on? Is it a chemistry book? Is it a science book? Is it... What are you working on there? As you guys can probably see, these superconductors are not lasting quite as long, and that's because they are really taking on a lot of water. So I'm not sure how much longer these experiments are going to last. The smaller one kind of gives me a clue as to how long I've got. Turn her upside down. You can watch how quickly it frosts over. As it frosts over, that sort of tells me that there's a lot of water in these. Oh yeah, sure. If you'd like, if you tell me exactly what you're looking for, I may be able to give you a couple chemistry experiments that I've published that, you might want to include in your book. I don't know if you're trying to write about experiments people can do at home or in the chemistry lab. You see this is frosting over quite quickly. A lot of Vamuri, a lot of salts just absorb water out of the air. It's a very common occurrence. It's called deliquescence. Deliquescence is a property where salts will just spontaneously absorb water out of the air. And as you can see, when that happens with the IBCO material, it makes it so that the superconductor doesn't work as well. All right, let's try this one. There we go. Get her on there. Get her on there. There we go. Spinning away. Yeah, you can see, wow, is that really frosting over quickly? Really fast. Oh, yeah. Oh, look at that. You can see the liquid nitrogen boiling off rather quickly. Yes, Vamuri, it can lose absorbed water. That's what I use the desiccator for. That if you're a chemist, you recognize what that is. If you're not a chemist, what this thing does, there's a salt down here that's highly deliquescent. So this is going to absorb any moisture that gets inside this sealed chamber. And so, what I'll do is I'll just take my superconductors when I'm done, and I'll pop them in here and seal it up. And the moisture in the superconductor will get absorbed by this material down here. This is like anhydrous calcium chloride. Boy, that'd be a good idea to seal it in a resin. Liquid nitrogen's boiling point is 77 Kelvin. In Celsius, that's negative 196. So if you watch, if I seal this up, the lid might pop because the nitrogen's going to continue to boil off. So if we hear a pop, that's just from the lid, popping off because the nitrogen's boiling off. But looks like this is still working. It's still working. Let's see if we can get this on the track, this one on the track. And then I think we might be done. I hate it, but my superconductors are just too wet. I don't know about that. I don't know if deliquescent materials can help prevent the, look at that. Boy, that's working well. If it can prevent the, the rusting of iron. Round it goes. Oh, it got caught. I think it's hitting the background I got here. There we go. Going around the track. Oh, it's having trouble here because that's right. I stuck a magnet there. Sunday morning science, Mocha, welcome. Yes, this is a Type II superconductor. That's correct. Oh, yeah, I got you, Duddy. Yeah, pop me in. I'd be honored. Thank you. Hey, it's Farah. Welcome back. My superconducting discs are starting to get a little bit wet, so they're having a little bit trouble maintaining their properties. It is extremely cool, and we've got this experiment working, so you can see that magnet levitating there on this superconducting disc. We got both of them going on at the same time. Got a little bit of nitrogen left for today. Oh, looks like this got warmed to above its critical temperature, so let me... Hey, 6 Savage 10. Hello? Pop that in there. Cool it down below its critical temperature again. Then we'll try to get this magnet popped on top. Let's get this thing moving. Get this thing moving around the track. Woo! Oh, that my magnet on, or my superconductor on the track got too warm. All right, we'll pop it here. And let's see if I can get this hovering. Ah! It's not the easy. I'd like push it, pinch it down. There it goes. There it goes. We got her rolling. Get that thing going. Isn't that cool? Just, that's spinning so fast the camera can barely pick it up. All right. I'm gonna get this and pop it in. Get that cooled again. Yes, this is moisture that's condensing on the surface, and unfortunately, the moisture also gets embedded into, absorbed by the superconductor. And when that happens, they don't work as well. And we're starting to get to the point where that's happened quite a bit. And so the discs are taking quite a bit. I wish I could do live more, but I got a job. I gotta pay the bills. But yeah, I enjoy doing these experiments. And thanks, you know why I enjoy them, because I get to see folks. This helps me connect with other people. So thank you for joining in with me on this Sunday and having some fun with superconductors. We got one more here. Gonna get this one out. I wish it could be used for trains, but unfortunately at this point, they only work at really cold temperatures. Thank you, Moon. But yeah, I mean, people are obviously studying, trying to figure out how to get these to work at room temperature. Man, if we could get this to work at room temperature. Oh, thanks, Vamuri. It's great to ask questions. Yep, I'm a teacher. And look at this over here. Ah, look at that. Let's get her rolling. One of my, someone who was following today suggested I use a straw to get the magnet rolling. So that was a really great suggestion. Look at that go. It's just beautiful. What an interesting effect. Thank you, Dutta. That was a great, great suggestion. Thanks for teaching me. That's what I love. I love when folks teach me new stuff. The problem is I do so many experiments, I forget. Unfortunately, I'm going to forget that little tip. I hope not, but I probably will. There it goes. Try to get this going one more time. That may be done. Yeah, I think this one's done. You can see it's no longer repelling the magnetic field. It's been warmed above its critical temperature. So let's pop it in the liquid nitrogen. I'm just popping it in right there with the magnet on it. Why not? See what happens. Boy, it's like stuck to it now. I wonder if that's because it just froze. Yeah, I think it froze to it. I think the magnet froze to it. Hey, thanks, Moonlit. I appreciate it. Vamuri, I think, it depends. I think I do other experiments other than chemistry experiments. Yeah, I've got, to me, it's all science. To me, it's all science. I tend to do more physics and chemistry. Well, Mocha, all superconductors have a critical temperature below which they become superconducting. And the material I'm using here is called an YBCO superconductor. And this particular YBCO superconductor has a critical temperature of 93 Kelvin. That's really cold. Fortunately, liquid nitrogen is colder than 93 Kelvin. So if I place that superconductor that you see there into liquid nitrogen, it gets cool below 93 Kelvin, and then I can show these superconducting effects. So these are not room temperature superconductors. They are, look at that, look what I did. You see this? I took the magnet and I just grabbed hold of it, and by doing that, I'm able to pull the superconductor out. Look at this. Look at that. It's not even touching. You see that? It's not even touching. That's crazy. And I'm going to just see if I can't just pull it and pop it onto. That is awesome. Now, unfortunately, I can't get my tongs away and hold the camera at the same time. Oh, I can't do it. Ah! There it goes. That was pretty cool. Let's try this. Here, let's just see. Let's see if I can do this. Thanks, Moon. That was a fun experiment, man. Let's see. Let's just see if I can just pull it up. Look at this. You can see I was moving the superconducting disc with the magnet. I'm trying to see if I can't pull it up. I mean, I'm definitely moving it. It's like a point. There it goes. I couldn't pick it up, but man, I could do it in the... Let's try it again. Let's try it with this one here. All right? I'm going to pop this in here. I'm going to stick this magnet right on top of it. All right? And then we'll try that experiment again where I can just pull it out by just using the tongs and the magnet. Let's watch this while that one's cooling. Get this rolling again. Oh, it's too close. Oh, there it goes. We'll just do it like that. Away it goes. All right, let's see if we can do this again. Yep. Sure. Oh! I don't know what's going on there. Is that even touching? I can't really see, and it's hard to see. Quantum locking is definitely fascinating. Okay, I will do that. I'll look that up. The FAQ science show, you said? Is that what... Oh. Let's see here. Woo, that's cold. Look at that. I got that one going too. Got two of them going at once. Two of them going at once. All right, folks. You know, I've been doing this an hour. That's about how long I plan doing Sunday morning science every round. I really appreciate you being here. Thanks for joining in. I had a great time doing some experiments. FAQ Science, I appreciate it, Dutta. I appreciate y'all being here. And, you know, be sure to check out my videos on my regular channel. And Tommy Technetium, leave some comments. Let me know you were here. I really appreciate it. And you all have a great week. So long. Bye, everybody.